Have you ever stopped to think about how your ideas, the thoughts in your head, actually turn into actions on a screen? Well, today we're going to journey through the incredible history of code. It's a story of how we, as humans, figured out how to talk to machines, going from these tiny electrical flickers to languages that look a whole lot like our own.
It all comes down to this one fundamental challenge, right? How do you take a complex, creative idea from your mind and explain it to, well, a box of wires and circuits? That machine, it doesn't get nuance or sarcasm or context. It only understands pure, simple, cold logic. And bridging that massive gap, well, that's the entire art and science of programming.
Just think about how we talk. Our language is fluid, it's messy, it's beautiful, packed with context and all these unspoken rules. A computer it can't handle that ambiguity. It needs absolute precision. Every single command has to have one and only one meaning. And it's all governed by this super strict set of rules we call syntax. If you get one little thing wrong, the whole thing just doesn't work.
So, to really understand this, we've got to go all the way back to the very beginning. Let's talk about the computer's native tongue, machine code. Yeah, to us, this just looks like a crazy wall of ones and zeros. But to a computer, this is crystal clear. Every single one and zero is a direct command. It's an instruction for its circuits to either open or close a switch, creating these tiny electrical pulses that make literally everything happen. This is as close to the bare metal as you can possibly get.
And believe it or not, it's not just random numbers. There's a structure here, a simple grammar. You've got the operation code, which is basically the verb. It tells the computer what to do. And then you have the operand address, which is the noun. It tells the computer where to find the data it needs to work with. It's like a super simple but powerful little sentence for the machine.
But, as you can probably guess, programming like this was an absolute nightmare. For starters, every program you wrote was completely locked to one specific type of machine. You had to memorize thousands of these numeric codes. And can you imagine trying to find a typo in that sea of ones and zeros? Forget it. It was slow, it was frustrating, and so easy to make a mistake. We desperately needed a better way.
And that better way, that first brilliant shortcut, came in the form of assembly language. The goal was pretty simple. Let's make programming something a human being can actually read without losing their mind. And just look at the difference. It's night and day. Instead of that cryptic string of binary, programmers could now use these simple, memorable codes called mnemonics, like MOV for move. All of a sudden, the code started to make sense. You could actually read it and see the logic instead of just staring at a stream of numbers.
Okay, but that brings up a really big question, right? If the computer still only gets ones and zeros, how on earth does it read a word like MOV? Well, the short answer is it can't. Not directly anyway. It needs a little help. It needs a translator.
And that translator program is called an assembler. Its one and only job is to take that human-friendly assembly code and translate it line by line back into the pure machine language that the computer's hardware actually understands. It's the essential bridge connecting our symbolic world to the machine's electrical one.
Now, don't get me wrong, assembly was a huge leap forward, but it still had this one fundamental flaw. It fixed the readability problem, for sure, but your code was still basically welded to one specific computer architecture. If you wanted that program to run on a different machine, you had to throw it all out and start over. We were still thinking at the machine's level, just with better words. And this brings us to the next great leap. This is where we start talking about languages designed not for the machine, but for the people writing them. This is where modern programming really begins to take off. The whole idea was just revolutionary. It was, what if we could write instructions using plain English words? What if we could use the same math symbols we all learned in school? The goal was to completely hide all those messy hardware details and just let programmers focus on one thing: solving the problem.
And the benefits were an absolute game changer. For the very first time, programs became machine independent. You could write your code once, and then with the right kind of translator, you could run it on all sorts of different computers. This idea of portability, it changed everything. You didn't have to be a hardware expert anymore. You just had to have a good idea.
Okay, so let's zoom out for a second and look at the whole journey. This table does a really good job of laying out the key differences between these different levels of programming. It's a pretty clear trade-off when you look at it like this. The low-level languages, they give you incredible power and direct control, but you're chained to the hardware, and man, are they difficult to use. High-level languages are the total opposite. They free you from the hardware, they're way easier to learn, and they let you build things so much faster.
The entire history of code is really a story of moving away from the machine and closer to the human.
So we've gone from raw binary all the way to languages that feel almost like having a conversation. And it really makes you wonder, doesn't it? Especially now with AI that's starting to understand our natural language. What's the next great leap? Are we even going to need to code in the future? Or will we just talk to our computers? What do you think the next evolution of code is going to look like?